We're looking at Euler's method for the solution of a differential equation. Now what we need to go back and look at is something from maths methods that you'll see, which is differentiation by what we call first principles. So the idea is that you've got a function, f of x, and that's in the graph here, it's shown in red, and you're looking at a particular point, x, so the function at that point would be f of x, and you're going to move across a really small amount, we call that amount h, so we move to a point x plus h. And what we're trying to do is make this distance h as small as we can. And so what we're trying to build towards here is actually sketching a tangent, because the idea is, let's say, just pretending that you had a point h that was here, you're going to draw a line between those 2 points. And the closer h gets to the point that you started with, the better this becomes as an approximation to the tangent or the rate of change at a particular point. So what we then do is look at the function at this point, x plus h, which is here, and that's x plus h and f of x plus h. So we've really got two coordinates that we're now interested in. And the idea then is to use effectively rise over run. So the triangle, looking at the slope of that triangle that's formed. So the rise, this distance here, is going to be the function height x plus h, take away this bottom part, or this bottom height here, which is the function f of x. So we subtract that. That gives us the height of this triangle. And then the distance of the triangle along the bottom, which is the run, is h, and we want h to be small. So it's effectively just rise over run, and that gives us slope. And so if you make the run as small as you can, that's going to get really close to being the tangent at that point. And so we say it's approximately equal to the derivative at that point, provided h is small. Now what we do with Euler's method is we're actually going backwards. So we're trying to integrate the differential equation. So what we're going to do is just fiddle with this equation here, which I'll put in a box. So this is what we call first principles. Now we're going to take the h over to the right hand side. So we have f of x plus h minus f of x is approximately f dash x times h. I'll put the h in front. And I'm going to go another step with that, and I'm going to just leave the f of x plus h and approximately equals h f dash x plus the function at x. And this is actually going to be what we use for Euler's method. The idea with this is that it has a few things going on. First of all, it's got a point, well, I'll just fix the x up there, a point x, which we're interested in, and that will be a point that's given to you. We have a point f of x, which is our y value, okay, for that x that you're given. We've also got the derivative here, f dash of x, and we've got an f of x plus h. Now the idea is we're going to start at a point f of x, so if we imagine there's f of x, we're then going to move by steps in the direction an amount h. So we get to the next point, which is f of x plus h. Then we get to the next point, which is going to be f of x plus 2h, and so on. It goes up and up. So the idea here is to try and find, using the derivative, try and find these points f of x plus h, so that we can basically sketch out a solution curve. So this is going to try and help us solve a differential equation, or a DE. So we're going to use this. So what we'll do is have a look here. First of all, we've got a differential equation, dy dx equals x squared minus 2x, and we have the point y equals 0 and x equals 3. Okay, so what I'm going to set up here is a couple of things. First of all, I'm going to kind of mimic this setup here. I'm just going to use a y instead of an f. So I'm going to have y of x plus h is approximately equal to h times, y dash of x plus y of x. Now we're going to need a few things here. First of all, the distance h that we move. You generally want h to be quite small, so h is called our step size, and a typical step size would be 0.1. Okay. We also need an initial x value and an initial y value. And we've actually got those in this differential equation. We have x equals 3, because that's been given to us, and the corresponding y value is y equals 0. Okay, So now what I'm going to do is simply substitute. I'm going to use these ones in this case. And what I'm going to do here is substitute them in. So I've got y of x, this is the x that we start with, so it's 3, plus h is 0.1, is approximately equal to h, 0.1, times the derivative, so it's x squared minus 2x, okay, and it's the derivative where we have, I'll just put it in here, x in there, so derivative at 3, plus y at the point 3. So it's going to be 0.1 times the derivative when x equals 3 will be 9, take away 6, and when y equals 0 when x equals 3. So this is going to be 0.3. Now at this point you probably think, and I'm just going to condense this down, so this is 3.1. What's going on? Well, first thing, we had 1 point to start with here for this differential equation. We had a differential equation and an initial condition. That first condition was a coordinate. When x equals 0, or I should say when x equals 3, y equals 0. That was this coordinate here. Well now, using this formula and substituting in the initial x, the initial y, and using a small step size of 0.1, check this out. This is another coordinate. When x equals 3.1, y equals 0.3. So that's another coordinate. I'm just going to I'll put the coordinates up here. Let's find ourselves another coordinate. These coordinates are solution coordinates. So let's look at the next one. I'm going to continue, this is iterative, so let's look at, we had 3.1 in the bracket, now let's add another 0.1 to that. That's approximately equal to h, which is 0.1, times, this time we're going to look at the derivative at 3.1, because we're moving everything up. And what's y at 3.1? And the cool thing is we actually know what y at 3.1 is, so we can put that in. I'm just going to use my CAS for this one. So we've got x squared minus 2x, and x is 3.1. So I'll have 3.1 squared minus 2 lots of 3.1. 3.41. So this is going to be 0.1 times 3.41 plus, and I know that y of 3.1 is 0.3. And if I put this all together, multiply 3.1 by 0.1, and I'm going to add 0.3 to that, 0.641. So after all that, I end up with 0.641. And that is another coordinate for our solution. So we're slowly finding coordinates. And if I look here again, this is going to be y of 3.2. So see, you're just going up in 0.2s. So 3.2, comma, 0.641. So you're sort of slowly sneaking along the curve of the solution. So there are 3 coordinates that would sit on the solution curve of our differential equation. Now if we go through that method, and again the next one would be 3.3, so you'd look at y of 3.3, and then you'd be looking at substituting y dash of 3.2 and y of 3.2, and you just continue that way. That's what we call iterative because it repeats itself. So if we were to sit there and do that for a long time, what we would find is a table like this. So this is the first part that we did. We had 3.1 and 0.3, and then for our next, so 3.1 and 0.3, then we had 3.2 and 0.641. So basically the coordinates we found for our solutions, the x and the y that we found from our derivative, this is the derivative here, these are the coordinates. First coordinate, second, third coordinate. So if you were actually to sketch these, you'd slowly build a solution. Now, we can check that because the differential equation we were looking at is this one. So dy dx equals x squared minus 2x. Well, we can integrate that pretty easily by hand. So we get y equals x cubed on 3 minus 2x squared on 2. So the 2's go away, plus a constant. And if we look at this table underneath, this table here actually tells you for the function that we've put in this table here is actually y equals x cubed on 3 minus x squared. These are the x and y values. So you've got your first iteration would be 0.3, and then 0.641 and 1.025, and you can see that they come up here as well. So there's a link between this function, x cubed on 3 minus x squared, and our estimation using Euler's method of finding those coordinate points. All right. So the idea is that we're going to build now upon this. So here's Euler's formula. So you can see that you've got your initial x and y values, and then you're building up those x and y values as you go using this formula here. Okay. Now, it is good to know how to do this by hand, but largely you'll use the CAS for this. So in terms of using the CAS, I'll show you next, in the next video, how to use the CAS for a problem using Euler's method to solve a differential equation.